Hi everyone, my name is Bruno Reis, and this is a presentation about Calphad Optimizer in FactSage 8.2. I will explain to you what this new module of FactSage is and how to be used in a demonstration. So, in order to understand what the program is, we can take a closer look at the Calphad technique itself. There are three steps that constitute this technique. The first one being the collection and evaluation of experimental data, either from the literature or from new experiments. And the second step is the setup of sensible thermochemical models. So this is when the database developer selects which model is better suited to describe a certain phase. And this is normally done in FactSage with the compound and the solution modules, both available from the main screen of FactSage. So yeah, and then there's also the optimization of thermochemical parameters, which means ideal solutions becoming real solutions and unknown properties becoming known normally, or at least with a better estimate for pure compounds. And so Calphad Optimizer helps in the third step by allowing a better optimization of, or a better control of the optimization process with many benefits. For example, you have access to all thermochemical models in FactSage, including quasi-chemical models. You have easy input of experimental data, for example, with predefined recipes and the test option. And there's access to different optimizers, two of them, the Gaussian process and the normal optimizer. And there is extensive feedback on errors per data groups or per data points. And there's even sensitivity of parameters to be analyzed. And other than this, or all of this actually, is available in an intuitive graphic user interface that I'm going to demonstrate to you right now. So I'm just going to open FactSage. This is the new version that is in the beta state. So you can already take a closer look at it. And you will see that there's a new button called Calphad Optimizer. And if we click here, we have two options. We can also open the previous version of a program that had the same purpose, which is called OptiSage, or we can open this new program that we're talking about today. So I'm going to click on Calphad to open the new version. It starts up, and there it is. So I'm just going to move my rectangle there so I don't get in the way. Just takes a little bit of time. There we go. And I'm going to present the interface. So you can see that the interface is divided exactly as the Calphad technique is divided. We enter the input of experimental data, we enter parameters that we want to optimize, and then we control the optimization and we check the results. So the first step is actually to load a database that has been previously set with the previous steps. So that has been set, sorry, in FactSage. And so, for example, here the program comes with some examples, and I'm going to load the sodium chloride, strontium chloride case that is in the DAT format. So the DAT format is one that can be exported from FactSage itself with any private database, and then you can load it here for use and for optimization. So there we go, with the database is loaded, and then we can start with the first step of entering experimental data. So you can see there is new group, load or save. Load, we can load preset data and we can save them. And if you are starting from scratch, you can click on new group, and then you can just define a case here. I'm just going to write test experiments because I'm going to show you more than one. Just give you a quick pick, and then I can expand them here. And then you can see there are different types of experiments to be selected in the first drop-down menu. And there is an explanation for each of those. So, for example, for the liquidus temperature, we can see a brief review here of what the liquidus temperature is, what it means, and then we can also understand a little better what we are doing. Let's say, for example, we are optimizing the zero phase fraction lines in a phase diagram. In this case, the liquidus one. So there is an explanation, and then if you look into the other drop-down menus, you have the actual fields that are required to use to define this recipe. So you need to let the program know what the liquid phase is, how many components you have, what are they. You can change the formula here freely. There's free input of formula, just like in the Equilib module of FactSage. And the pressure can be constant or variable. And then you also select which phases are going to be part of this calculation. And then you can also enter as many data points as you have gathered from the experiments. And that's about it. And yeah, and then I'm going to tell you quickly about the other cases. The solidus temperature, it's not really much different because only the calculation itself looks at another variable, but everything remains the same. It is quite similar to the liquidus temperature. It only has a different target there. Other than this, we also have the heat of mixing with easy input. So this is when we have two species, two chemical species mixing together, and then there's the overall heat released or absorbed, depending on the case. Actually, released as a negative amount and absorbed as an endothermic heat of mixing. And in this case, it is meant to be used for a single phase, so it is the heat of mixing of a phase, and then you need to provide the name of that phase. But you can select different reference states for the input components. So if I have two of them here, I can select different components, and that will be taken into account. Sorry, when considering when performing the calculation. For example, the pure liquids into the liquid solution. We can then again define the temperature, pressure, and the data points. And then other than this, there's also the enthalpy increments. I'm taking a little bit too much time, so I'm not going into much detail there. I can just show you briefly that this looks like this. Is the variation of enthalpy as a function of temperature. So these are the ones that we have preset. The other option would be to define the conditions of the calculation yourself, which is a bit more similar to what the Equilib module does. But this is done now here in an interface that is dependent entirely on a table. So you can either remove conditions or add them. And then you can also have one measure variable or more than one to be considered as a target for your calculation, for the optimization actually. And then it depends, but I'll not spend too much time on this. So I'm just going to close this one, and I will load an experimental data set that is already available for the system as an example. So sodium chloride, strontium chloride. It is loading. It takes a little bit of time to generate all the different properties there. But then once it is there, you can see there are many data points here. And what we can do is that we can test this to check if there is any sort of problem. It does say success, which is good. And it means that the calculation can be performed. So it is a good set of data to be used for the optimizer. So with previous experiences, we know that this is not something that is available as easily in other tools that are meant for the same purpose. So what else can I tell you? You can also take a look at details here to check on calculations. And just as we have for the Equilib module, you can take a look at the stability of all the phases in this system. But in any case, we have what we need to get going. The next step then, after having the experimental data, is to define the parameters of the system. So there are different options here. We can select compounds, functions, or solutions. So I'm going to select, for example, the sodium chloride solid phase, and I want to optimize, let's say, the heat of formation um, of this compound. So I can just click on optimize, and then we can take a look on the bottom of the other block. You can see that it is already added to the list of selected parameters. And then we could also select other ones. We can also take a look at the plots for the different properties. This is all very easy to manipulate and to use. So you could also change the values directly here. I will not change them because I want to optimize them directly, but it's really not a problem. And then for the liquid solution, I want to optimize the interactions between the two species. And this is a Radich-Kister polynomial. So I want to optimize the L0 term with the A coefficient and the B coefficient. And I also want to optimize the L1 parameter with the A and the B coefficients. So you can see there are different variable names being assigned to each of those parameters because they now become a variable of the optimization for the optimizers. And then when we move down here to the next block, which is called optimization, we can see all the experiments that have been added to this system, to this optimization. And we could deselect a few of them if we want to optimize stepwise, right? Or if we want to address any issue that we realize in the middle of the process. But for now, we select all of them. And the same goes for the selected parameters, with the difference that in this case, we can also change the values directly here. And we can also change the minimum and the maximum values that are set here by default. I'm going to change them by 1 order of magnitude because it would take too long of a time for this presentation. In every case here. And also, of course, it should give us a good enough result for this demonstration. So that's it. The minimum and maximum are reset. And I'm just going to leave this default settings for the optimizer. This is using the chain of Gaussian process, but you can also select Nomad. And for each of those, you have the hyperparameters that can be changed. There is an explanation here of how this works, of how the optimization works for the Gaussian process. So this is all very interesting, but we need more time for that. For now, I'm just going to click on Optimize. And you can already see something going on here. The optimization has started. There is something called batch evaluation in both cases. I can also click on results to follow what's going on, what are the changes. And this is very nice because you can already see all the plots of the calculated variables, the calculated values for each experiment against their measured values that have been set as a target. So what we want is to fit those values as best as possible, right? We want those curves or those dashed curves to go through those blue points. And yeah, we can already see quite quickly that the optimization is progressing well. The activities are well for the strontium chloride. We have the liquidus temperature on one side, and on the other side, with a good agreement, the heat of mixing of the liquid solution also being very well described here. And the only thing that it is actually taking a little bit more time to fit is the eutectic temperature. So there's a difference here of about 4 degrees Celsius. But while it continues to calculate to try to improve that one, we can also take a look at the new values, which are updated dynamically here. We can already use them or read them from this table for the parameters, which is the main purpose of the program. And there are a few other things that we can analyze. We can also check the optimization progress as a chart. So we can see how the error evolves against each evaluation. We are now at evaluation 177, so it is still going. And we could as I'm doing here, just zooming in this chart to check a little bit more of the errors, which experiment might be contributing more to the error. So there's a lot of analysis that you can do based on these charts. Yeah, the difference now is about 1 degree, depending on the point. So, but it's much better already. So this is already a good optimization. And the last thing I want to show is just a distribution curve for or distribution of points for all the parameter values that have been tested. This is very useful for some analysis, and you can check some correlations between all the values tested and the error being resulted overall. For example, here there's a sort of a curve here for the V2 variable, which is L0A, which indicates that the best value is around minus 4,000. And this is probably the value that is there on the top. Yeah, minus 360, sorry, 3,600. But this is about it. I think this is enough at least for us to discuss. And I'll stop the optimization right now. And I thank you for your time. And yeah, I'm open for questions. Thank you.